Okay, we're very happy to welcome Jose Perea from Northeastern to talk to us today about approximate vector bundles.
Yeah, thank you for the invitation. So where do we start? Yeah, data. So typically the idea or the premise is that data sampled in scientific applications has geometric structure or underlying geometric structure to it. And the question is, can you compute something interesting? So the typical sort of vehicle for computing sort of shape descriptors for data is something like the Ribbs filtration, which is sort of this family of simplicial complexes where your data is just a finite metric space and you are using distance predicates to include simplices. Okay, so this is sort of the simplest construction. So given a filtration capturing sort of the multi-scale structure of your data, one of the things you can compute is the cohomology, and in particular, the persistent cohomology of the filtration. So this is just a family of vector spaces and linear maps between them. With a little bit of linear algebra, one can show that there are compatible bases across these vector spaces. By compatible, I mean that two basis elements go to two distinct basis elements, or they go to zero, right? So if you only look at these two vector spaces, this is what Gaussian elimination does for you. It finds sort of nice bases for your linear map. This is what we use all the time in topological data analysis. This is what is called the barcode, just sort of a sequence of basis elements chosen in such a way that you can track topological features. Another way to understand this statement is by thinking of the following setup. What I've constructed is essentially a functor, let's say V, from the category, the posed category I less than or equal to, where this is where your indexes live, your distance thresholds live, to the category of finite vector spaces. And what one can show is that two such diagrams or two such functors are naturally isomorphic if and only if their barcodes are the same. Okay? So again, if you go back to this picture, essentially I'm saying if you forget about all these other vector spaces, two vector spaces are the same if they have the same dimension. If you look at two vector spaces, the diagrams are equivalent if they have the same dimensions in the domain and the range, and they have the same rank. And then if you look at a longer chain of vector spaces and linear maps, the barcode is the thing that subsumes the algebraic structure. Okay? Pretty. And then the typical visualization is sort of, start with data, compute the Ribbs filtration, and then compute persistent cohomology represented as barcodes. So you all probably have seen this many, many times, or at least once before. So here's another way to represent the same information, and it's through the persistence diagram. So instead of intervals or bars, which again represent these choices of compatible bases, you can just record the endpoints of each one of these intervals and put them in a scatter plot. This visualization is typically more useful in machine learning, and I like the barcode when I'm thinking about the algebra behind it all. Quick question.
The finite field, what is it?
Finite field. So
The F?
yeah, the F is just any field.
Any field?
Any field.
Oh,
And I'm just asking for my vector spaces to be finite dimensional,
okay.
right? In computations, F is going to be a finite field, like a Z mod P. Okay? Yes, David.
BCD's barcode and DGM is
Diagram. Yep. Yep.
Is there a reason why you said this is a co-mono? Like, why emphasize the co? You just have to make a choice.
Yeah, so I mean, it turns out that because we're working over a field, persistent homology and cohomology give you the same barcodes. This is the universal coefficient theorem at play. It turns out that cohomology is more useful for things like vector bundles. It turns out that the cohomology computation is faster than the homology computation, but they give you the same answers. So there are many good reasons for choosing cohomology. Yeah. Yeah. Okay, so here's a sort of a silly example. So a bunch of little duckies in different positions. So that's the data set. Here is the persistent cohomology of this data set. And hopefully what you can see is that you have sort of two classes, one in dimension 1, one in dimension 0, which is telling you that the data is likely connected and it likely has a hole in dimension 1. If you do a little bit of dimensionality reduction just to check, that's the result of doing principal component analysis on that data set. So what I've done is I just projected the data from this high dimensional space to a well-chosen R3. And this is what the projection map looks like when you overlay the duckies where in the coordinate they are supposed to lie. So it is completely consistent with the persistent computation. And if you couldn't do the dimensionality reduction, the persistence diagram suggests that the data likely lies along a circle. Okay? So that was the sort of persistence introduction. So what I want to do next is, okay, so we can compute things like persistent cohomology. Yeah.
I really like this example. How general is this in the image or in just in the 3D object you pick to rotate? Can you pick basically any arbitrary 3D object and rotate these images and get the same sorts of results?
Yeah. So for example, if you're, so any geometric object, and let's say that you act on it by some sort of group of symmetries. So if your group is not symmetric, then you're thinking of the orbit of the space. And that should be reflected in the collection of.
And this bears out experimentally. Like
Yeah.
how broadly have the experiments done? Have they just used this image? Or
No. I mean, we've run other experiments. Yeah, we've run other experiments, but
That's really cool.
yeah, but who knows, right?
That's cool.
Yeah. I mean, this is useful to again, to think about objects with symmetries and groups acting on them.
Yeah.
Yeah. Okay, so the next thing I want to do is, just like we computed persistent cohomology, which is, again, a data analog of cohomology. And we have theorems that say things like, if your data samples, let's say your manifold well enough, and the persistent features are far enough from the diagonal, then you can recover the cohomology of the underlying space from this persistence diagram. You have sort of recovery theorems. The goal now is let's see if we can compute other stuff, such as vector bundles. So that's what I want to do next. Okay? And just to remind you, a vector bundle is a triple, EBP, where E is the total space, B is the base space, and P is a continuous or surjective map. The fibers of this map are supposed to be n-dimensional inner product spaces. One comment here is that I really want the inner product to be part of the definition. In data science, you typically have these things. If your space B is compact, you can always put some inner product. So we might as well just start with it. Okay? Those are called Euclidean vector bundles. And then it is possible to trivialize around any B, and then you can choose the trivializations to be fiberwise preserving, and again, linear isomorphisms on each fiber, right? Just to remind you what a vector bundle is, right? Just a bunch of vector spaces parametrized by this B. And again, I'm asking that each vector space has an inner product, and that inner product varies continuously with B. Okay? So that's what a vector bundle is. Here are some examples that are very useful to keep in mind. The first example is the tangent bundle to Riemannian manifold. So again, B, your base space is a manifold, and then over every point X, you have the space of derivations or sort of tangent vectors, the derivatives of all lines. And then you just put them together, and that's the tangent bundle. Another example that is going to be super useful later is the normal bundle to a smooth immersion. So suppose that B and M are Riemannian manifolds, and that iota is a smooth immersion. What I mean by that is that the derivative, that the differential of I is injective at every point of B. So it's full rank, okay, at every point. And then you can define the normal bundle, which is TB perp iota, which is essentially the vectors that are tangent to M and orthogonal to the tangent space of B. Okay? So again, that's going to be useful in a moment. Yes, David.
Well, this is a dumb, naive question, but if I have a manifold with boundary,
Mm-hmm.
is the normal bundle to the boundary the same as the normal bundle to the boundary, as in if I embed it into some Rn?
So you have to tell me with respect you're taking with respect to what you're taking the normal bundle.
Right.
So if you're saying I have the boundary and I'm going to look at the normal with respect to the manifold that it contains, then it doesn't depend on what space contains M, right?
Yeah. Okay.
Again, here I'm saying like choose your target and take the normal with respect to that target.
Yeah. Okay.
Yeah. So here's the third example. This is the Grassmannian manifold, which I like to think of as the collection of M by M matrices, which are symmetric, are essentially sort of orthogonal projections of rank N. Okay, that's one way to think about them. Let me rant about this for a moment. So the typical way people define the Grassmannian is you start in Rm, and you're asking for all the n-dimensional subspaces of Rm, right? If I give you an m-dimensional subspace, then there is certainly an orthogonal projection map. And you can write down the matrix for that map. That's P. Okay, and it's a one-to-one thing. If I give you the matrix P, you can think of its column space. That gives you this thing. And if I give you the space, and you give me any sort of any orthonormal basis, that gives you P by taking like, how do you do it? So if these are like U1 through UN, and the matrix U is like U1 through UN, then you can take U times U perp, and that's P. So whatever description you like better. And then the Grassmannian has what is called the tautological bundle to it, which is at any point of the Grassmannian, meaning at any P, you're going to put all the vectors in its column space. Okay? And then the projection is just give me the projection matrix. Okay, so that's another vector bundle. And here is sort of the last example, sort of a construction rather. If you have a vector bundle over B and you have a continuous map from another space B prime to B, then you can pull back the bundle from B to B prime. The total space is the collection of points B prime E, where B prime is in the fiber over P of E, over F of B prime. Okay? So you're sort of, again, pulling back the bundle. Okay, so after these examples and constructions, we come to this sort of fantastic theorem, right? If you start with a compact or paracompact topological space, then the isomorphism classes of vector bundles over B of dimension n are in one-to-one correspondence with homotopy classes of maps to the Grassmannian. Okay? And again, the construction is, if I give you an F, then you can pull back the tautological bundle over the Grassmannian. That's the construction. And this is invariant under homotopy equivalence of F. Yep.
Going into higher dimensions here, I've lost track of the rubber duckies. What is the connection with data analysis and this?
Yeah, so what I would like to do, and I'm going to give you an example in a moment, is I want to replace B by a data set and still be able to talk about vector bundles over data and compute stuff for them. Let me give you an example as to why that may be relevant. So the no, great question. So the question I have in mind is sort of tangential estimation. So let me show you a construction that people do in data science, something that people utilize in data science often. So suppose that I give you a data set in Rn, the little duckies. So something you can do is for every point in your data set, you can look at the k nearest neighbors. So the region in green for X and the region in, what is that? Pink, red for Y. And what you can do is you can compute, you can just do principal component analysis on each one of those regions separately. The idea is that the number of principal components in this region is, first of all, an estimate of the local dimension of the data. But second, the principal components act as a quote-unquote basis for the tangent space. This is all sort of intuitive. I'm not formalizing anything. So I'm just saying that if my data really does come from a manifold, then I would expect that locally, the principal components are a good estimator for a basis of the tangent space. Okay? People have formalized this in some ways. The thing to note is that this gives you a map from the data, the sort of local PCA gives you a map from the data to the Stiefel manifold of n frames in Rn. And if you take, again, the column space, this gives you something in the Grassmannian. Okay? So here's where we pause and think. A moment ago, I said that anytime you had a paracompact topological space, and I gave you a map to a Grassmannian, that was the same thing as a vector bundle over my space. And here I've used sort of local PCA to construct what should be sort of the tangent bundle at X. And all this should be and ought to be is, of course, not mathematical. And what we want to do is formalize this notion, okay? This type of construction. The type of examples I have in mind are from dynamical systems. So this is the double Geyer dynamical system. It's sort of two vortices that are swaying. Those are the equations if you like that kind of thing. And those on the upper right are the attractors of the blue and red particle, okay? So I went ahead and computed the persistence diagrams of those attractors, and I'm focusing on this region, which is where the topology lives. The thing outside of this region is sort of is the way the attractor is embedded in Euclidean space, okay? So what are we getting? We're getting that there is one class in dimension 1, so it is likely circular, and the same thing is happening here. But you would like to know more about the attractor, right? Not only its topology, but something like, is it a cylinder? Is it a Mobius band, right? So the hope is that one can compute tangential information about the attractors to get a handle on what attractor am I looking at. Does that make sense? More or less? Okay.
Are the computations very difficult?
No, at least for these examples, they're not. They reduce to computing determinants, essentially.
What space are you drawing the attractors in? 'Cause
Yeah, so
those are just in R2.
no, this is like R5, and I'm just projecting into R3 with PCA.
Oh, I see. There's
Yeah,
much more.
yeah. The intersections that you're seeing here are not intersections. It's just an artifact of the projection. Okay. So that's the hope. The hope is, can we compute something beyond cohomology? Can we compute something like characteristic classes to figure out what the tangential information about these attractors can tell us? Okay? So that's the first sort of motivational line. And we'll come back to this example later. So here's another type of construction in the land of vector bundles. So is the following. Suppose that I give you a topological space B covered by open sets Uj, and then on every non-empty pairwise intersection, I give you a continuous function to the orthogonal group of n by n matrices, and I'm going to request that the following equation is satisfied on empty triple intersections. Okay? Omega ij times omega jk is equal to omega ik. So this is called the co-cycle condition. The co-cycle condition. So if you have this type of data, you can construct a vector bundle over B using the following recipe. So essentially what you do is you take a copy of the Euclidean space Rn over every Ui, and then you use the omegas to glue together the Rn's. Okay? And the idea is that if these omegas are non-trivial, and I'll say what that means in a moment, then the vector bundles that you're getting here are non-trivial. Okay? So here's another way to say what I just described. If Z1 U ON is the collection of cocycles, then this construction gives you an arrow from cocycles to vector bundles over B. Okay? Here I really mean, here I don't mean coefficients in ON, I mean the coefficients in the sheaf of ON valued continuous functions. Okay? Just to make that clear. Here's again, just a beautiful, beautiful theorem. Again, if B is paracompact, and if you compute the first check cohomology of B with coefficient in this sheaf, again, the sheaf of ON valued continuous maps, then that is the same thing as isomorphism classes of vector bundles over B. Okay? Again, the recipe is you give me these omegas, and I'll just use them to stitch together locally trivial information into a big vector bundle. Okay?
Should we be thinking of categories here?
Categories, categories, categories.
I mean, where do the vector bundles live?
Yeah, so these are vector bundles over B,
Yes.
right? So, I mean, you can think of the category of vector bundles over B. That, yeah.
You get a categorical equivalence, I guess, as also with the first theorem, usually
Oh, I see.
classes.
No. Again, I'm thinking of, I mean, the reason why I say no is because I'm fixing dimensions. It's like n-dimensional vector bundles over B. To those, I can associate cocycles. You know, you can think of those as things in a pre-sheaf of ON valued functions, but yeah, it's not quite. Yeah, no, sorry, I don't have a better categorical answer. Should have prepared one, given that I'm coming here. But here's a sort of a source of data examples for this kind of construction. And it comes from synchronization and denoising problems. So here's the idea. You know, imagine that you have an object, like a molecule, and what you have is not the molecule, but photos from different directions. So this is the input data. Okay? And the goal is to reconstruct the molecule from the observed pictures. What people typically do is, because the images are very, very noisy, they try to group them together, sort of images that are similar, they group them together and take an average in the hope of averaging out the noise. Okay? So that's the hope. So again, for images xi and xj, what they typically do is they find the best alignment omega ij, just a rotation, okay? Now, let's go ahead and define this procrustes distance, which is just the distance in just matrices once you align the images as best as possible, okay? And again, the idea is that if you align a bunch of these images, you can average the noise out by taking their average. So what do we expect? We expect that if the distance from xi to xj, j to k, and I to k is very small, epsilon, then aligning I with k should be similar to aligning I with j and j with k, right? We've seen before what this kind of structure is. So this looks like a co-cycle condition associated to this topological space. And then the condition that we get is that the bundle that this defines, or if it defines a vector bundle, the bundle is trivial if and only if all the images can be aligned at the same time, okay? And the obstruction to being able to align all those images at the same time is given by the vector bundle not being trivial. It's exactly the same thing. So the message is sort of multiple alignment problems naturally lead to bundle questions, okay?
And you probably don't expect the bundle to be trivial, right? Because
Yeah.
you can't just two-dimensionally rotate.
Yeah, that's what you would expect. Yeah, but if you don't know and you just try to do it, you can. Sometimes you shouldn't. But so what do we have so far? Again, we have sort of these equivalent description of vector bundles over B as sort of co-cycles and maps to Grassmannians. That's what we have so far. And I hope to have convinced you that there are examples in data science that feel like vector bundles, but not quite because you have these errors, right? Like, we don't expect in data to have co-cycle conditions be exact because of errors. So we expect some epsilons. And in data, for example, in this tangential estimation, we don't expect to land on the Grassmannian exactly, but on some delta neighborhood of it, okay?
Do you know epsilon in advance, or do you estimate?
This is something you can estimate from data, right? You have the images, you can align them, that gives you the epsilon. So yeah, the goal is to, and this is what this paper does, is to see to what extent these things do align with vector bundles in the classical sense. Do you have a comment?
So what does it mean that it's like this delta thing? Does it mean that they're not really on the plane?
That they're not really
They're like a
on the
little
yeah, they're a little off from the Grassmannian. So.
What do you think about in terms of plane?
Yeah, so I think of it, I mean, remember that at least in this example, these planes came from PCA, right? So when you do PCA, you do have a bunch of, you are diagonalizing, you're taking the singular value decomposition of the covariance matrix, and what you expect is that the first n are going to be very strong, but then the other ones are going to be very tiny. That's what I expect to see in a PCA computation. So that's what I think. That's why I think of this map as not landing exactly on the Grassmannian, which would be all these other things 0, but in some delta neighborhood of it.
I see. So you're thinking that you're not truncating your PCA?
Yeah, like who's to say that I know where to truncate it, right?
That's a whole problem.
Right. So, but what you do hope is that, if the local dimension really is n, then your PCA has sort of a lot of information in the first n singular values, but then it drops off. So it's some neighborhood of the Grassmannian. I mean, also, even if the PCA is like super, super nice, we know that that PCA is not stable, meaning that if I add an outlier, the PCA really shifts. So again, neighborhood, okay? So again, can we do vector bundles for this type of input? So let me tell you what the paper, some of the results from the paper. So if I give you a simplicial complex K, we're going to define its discrete epsilon approximate cocycles as the following set, okay? So for every edge in the simplicial complex, I'm going to give you one of these orthogonal matrices, omega ij, in such a way that if I flip the orientation of the edge, I get the inverse. But then on triangles, I only get an epsilon approximate cocycle condition. Okay? So you can immediately define from this a sort of epsilon approximate cohomology, where you take these approximate cocycles and you put the following equivalence relation. So this looks like a co-boundary type of relation, right? So you're saying that omega is equivalent to omega tilde if and only if they differ by a co-boundary in a sense. Okay? What is cool here is that your coefficients come with a metric, right? So you have the Frobenius norm on matrices. So you can actually put a norm on these cocycles. So we can think about when two approximate cocycles are similar and when two approximate cohomologies classes are similar. So here's the first theorem we prove. We show that the classical map from cohomology to Grassmannians can be extended to the level of approximate cocycles in such a way that you don't get maps to the Grassmannian on the nose, but you have to go to some fattened version of the Grassmannian. Stably here means something else. It doesn't mean like in the homotopy theory sense of stable. Stably means that if I have two approximate cocycles that are very close, then the maps I get here are homotopy equivalent. Okay, that's what approximate means. Yeah.
Where does the square root of 2 come from?
Yeah, so it comes from the following. So again, I'm thinking of the Grassmannian as these M by M matrices, right? So this is a subset of R M cross M. And then I'm taking the column as M goes to infinity, right? So you get N R infinity inside of R infinity cross infinity. Again, I'm thinking of these as matrices, like infinite matrices, with only finitely many non-zero entries. And I'm asking, what is the reach of this space inside of this? In other words, I'm asking how much can I fatten it and still be able to deformation retract it? So that's where the square root of 2 comes from the sort of the reach of this space inside of this other one. Okay. The cool thing is that if epsilon is very, very small, I mean 0.5 or less, then this actually deformation, this is where the reach computation comes in. This deformation retracts onto the Grassmannian, which is the right-hand side. Okay? So you recover the old vector bundles, right? Which is cool, right? You can associate to any approximate cocycle like an honest to goodness vector bundle. In other words, the one that is closest to it.
And that epsilon is completely independent of K.
Right. So it comes from the approximate cocycles. The thing that I say can be measured from data, right? You give me your images, I align them. Epsilon turns out to be 1/4, and I'm like, great, let's go. That gives you a vector bundle.
Yeah, I was just commenting that it's cool that epsilon less than 1/2 is a bound. It's independent of any.
Yeah, it's a universal bound. Yeah.
Pretty well.
Okay. Here's sort of the second theorem we have. Suppose that I give you a manifold M in Rn, and then again tau is the reach of the manifold. And now suppose that I give you a vector bundle over M given by a map that is Lipschitz. Okay? So again, just think of this as a vector bundle over M, but given by sort of nice Lipschitz data. Now, what I'm going to do is I'm going to approximate the manifold M with a point cloud X, and I'm going to wiggle the map F to some other map G. Okay? So not only am I giving you the manifold in terms of data that is imperfect, but I'm giving you the vector bundle in terms of this map that is also imperfect. Okay? So X approximates M in terms of epsilon, and G approximates F in terms of delta. Okay? Perhaps if you really want the details, I'm thinking of X and M as being epsilon close in the Hausdorff distance, and I'm thinking of G and F as being close in sort of L infinity distance. So if alpha is some number in an ugly but specific range, then the following is true. We have this homotopy commutative diagram where the top is our sort of old vector bundle. The bottom is something we can construct from the input data, and the columns are homotopy equivalences guaranteed from the choice of alpha in this range. So this is the check complex, some simplicial complex one can construct from the data, and this is again an arrow one can construct from G. So the fact that this diagram is homotopy commutative and that this is a homotopy equivalence tells you that this is another description of this vector bundle. So you can recover F from data. Okay? And then finally, we have algorithms for computing the first few characteristic classes. So the Stiefel-Whitney classes and the Euler class. Again, given these approximate cocycles. Okay, so let me now go back to the data examples that motivated this pursuit. So again, here's the double Geyer, the attractors, and then the persistent cohomology computation. So here's the first thing we did. So go ahead and apply local two-dimensional PCA over every point of the attractor, okay? And now take omega jk be the transition function or the alignment between the PCA at J and the PCA at K. Okay? Again, just think of this as aligning the bases over this, over xj to the bases over xk. Okay? So now that is going to give us an approximate cocycle. The epsilon is 2, and we're just going to take the delta as large as possible so that this is still a 2 approximate cocycle. This is just so that we can apply our algorithms for computing the Stiefel-Whitney class, which we do. And then the final thing we do is we decompose this cohomology class in terms of the persistent cohomology class of the data, the persistent cohomology basis. So I'm just going to show you the results and explain very slowly what we're computing. Okay. So let's start here. Remember that every dot in here is one of these bars in the barcode, right? I'm just plotting the endpoints instead of the bar. Second thing, remember that each one of those bars represents sort of a choice of bases that is consistent across the scale. So what I'm saying here is that omega 1 is the linear combination of this basis element and then these other basis elements. Okay? In particular, this class is persistent in the sense that this very long bar participates in its expression. The same is done for the other attractor, but no basis elements are picked up. That means that the coefficients are all 0. The conclusion is that omega 1 is non-zero for this attractor, and omega 1 is 0 for this attractor. And what we know from topology is that a vector bundle is orientable if and only if omega 1 is 0. So what you conclude is that this vector bundle is non-orientable, and this vector bundle is orientable. I mean, the tangent bundle that we're estimating. Okay? And then this is done from data, and the only thing we're doing is computing PCA and determinants. Going back to the sort of molecules and rotations and all that, just to remind you, we expected that the rotation matrices will satisfy an approximate cocycle condition, and that you could align all those images if and only if the bundle was trivial. We repeated the same process, but this time computing the Euler class of the associate bundle, and what we got is the following. This is the Euler class of that bundle. So it's something very non-zero, okay? So in particular, the bundle is not trivial, which is exactly the intuition you had, right? That it's now possible to align all the images. Another way to think about this is that we're asking about the tangent bundle to the sphere, which we know is not trivial, okay? So I have, let me give you the preview of another paper that applies this technology, and we can talk about it if you're interested. So the paper is Fiberwise dimensionality reduction of complex data. And the goal is to understand or being able to do dimensionality reduction for things like conformation spaces of molecules. What we mean by that is the following. So take a molecule and realize it in Euclidean space, in R3. And then think of two realizations as being equivalent if you can go from one to the other via a rigid transformation, okay? And people are interested, and by people I mean people in computational chemistry, are interested in the topology of these conformation spaces, because that's where you do, protein folding, right? Energy minimization. So here is the persistence cohomology of the data set for pentane in dimension 1, right? So you get a big hole. Yeah?
You say for protein folding, you expect a rigid transformation of the molecule?
No. I'm saying that the space of conformations is the quotient up to that equivalence.
Oh, okay.
So different conformations, yeah. Okay, so this is the persistence diagram in dimension 1 for that data set. So you see sort of a very prominent loop in the conformation space for pentane. Here are the results of well-known dimensionality reduction methods applied to this data set. So again, what we did is we first did the dimensionality reduction into R3 and then computed the diagrams, okay? And again, what you can see is that isomap completely destroys the topology of the original data set, and Disney sort of hallucinates another class that wasn't there, okay? And this is what we are able to do with the vector bundles technology that we have developed. It turns out to be a Mobius band, and that's what shows up. So this is a really cool example, right? Like a small molecule, conformation space, non-orientable, right?
So are you using this tangent bundle approximation computation to decide what projection?
No, I'll tell you what we're doing. So the idea is the following. Suppose that you have some way of coming up with a map from your data to some manifold. So this can be the first step in a manifold learning approach, whatever algorithm you like. For the case of the Mobius band, we have ways of encoding this class as a map to the circle, okay? So we actually do that. We take this homology class and I mean, if you're curious how that works, is the following theorem. If you compute the cohomology of any CW complex with coefficients in Z, that is in bijective correspondence to homotopy classes of maps to the circle. Nice, right? So it says that anytime I give you a cohomology class in here, you can replace it by a map to the circle, and this is done up to homotopy in F. So we essentially, we have code that mimics this theorem. So we take this class and we turn it into a map to the circle. Okay, the second thing we're going to do is we're going to embed our base manifold into some Euclidean space, RD. So again, for the Mobius band, which we're mapping to the circle, and now we're embedding the circle, say, in R3 as the base, okay? And this is iota. And this is B, I guess. So now, the next thing we do is notice that we can think of B cross RD, the total space, the ambient space. We can decompose it as the tangent space to B, and the normal bundle using this embedding, right? So this is what we did before. So let me just show you what the goal is. So we have this initial map F that accounts for the sort of large-scale topology of the data, right? A circle. We have this second map iota that embeds the base manifold into Euclidean space. And the thing to realize is that, or the thing to look for is a way of improving iota so that the fibers of F can be laid out in the orthogonal direction to B. Okay? That's sort of a mouthful, but that's the goal. Again, you sort of improve iota so that the fibers of F are not crushed, but rather laid out in the orthogonal space to B. In other words, you want these directions. The way we do it is as follows. Go ahead and give me an open cover of the manifold and pull that back to the data, these regions xj. And now in each piece of the data, or each fiber, you can do dimensionality reduction separately. And again, the idea is that the horizontal direction of your dimensionality reduction is sort of the tangent direction to B, and the normal direction is what you've forgotten using F. So that's the Fiberwise normal. And now the goal can be updated to the following. We want to embed the Fiberwise normals as a subspace of the normal bundle to B. And here's where the vector bundle or approximate vector bundle technology comes in. So we can think of this green stuff as an approximate vector bundle over X, and the perp stuff as another vector bundle. And the cool thing we prove in the paper is that what we really want is to embed the green bundle into the purple bundle. And now we can use topology, right? We try to solve this embedding problem, which leads to an optimization over the Stiefel manifold that we can solve. And then if the problem has a solution, we have obstructions using the Stiefel-Whitney classes of the green and purple bundle. And then let me skip this just to show you the examples. Again, this is what we get by first taking the circular coordinate, which is this step, and then by aligning the normal directions using the bundle theoretic constructions we have from before. Here's a cool visualization, which is if you go ahead and unroll the Mobius band, these are the conformations that lie around these spots. And this is actually an estimate of the energy of those molecules inside of the conformation space. So we were able to do dimensionality reduction to visualize the conformation space and also the energy landscape for the molecule, which again is supposed to be hard. But, So those are the papers that, yeah, thank you.
Thanks, Jose. Questions?
Yeah, let me put that image back.
Did someone do some applications on actual data that check out how difficult it was to reach conclusions?
So, I mean, this is 2023, right? So we're waiting for people to take this stuff and do what you're saying.
How did you get the idea in the first place?
I don't know, it's sort of the topology brain, right? Like every time you see alignment problems, that to me looks like a bundle question. And at least to me, it looks like a bundle question. And you know that you're not gonna get exact bundles, but things that are, prone with a lot of errors. So you better adapt the bundle techniques to the error world. Yeah. Yeah.
So the techniques in the first paper seem mainly to be like super general and apply to any kind of shape your data might have. And the second paper, it relies pretty heavily on the fact that you get an S1 for first cohomology, doesn't it?
Right, so I guess instead of this vertical arrow F, so the question is, my data set can be whatever, but if you have a map to some manifold that accounts for the large scale topology, you can worry about dimensionality reduction just in the fibers, and then use the bundle theoretic stuff to align the fibers in some nice way, right? So instead of, again, trying to recover linearity everywhere, which is like things like PCA do, or try to recover distances everywhere, which is something like isomap would do, this is advocating for work on the fibers. Work on the fibers and then align the fibers using the bundle theoretic stuff, because, yeah, alignment to me sounds like a bundle problem.
So you could plug in this Fiberwise technology to some other way of getting a large scale map then.
Yeah. So this was very specific to this data set. We got lucky that we got a sort of a large H1, but I guess this also speaks to there are not a lot of tools that construct F for you in a way that preserves the global topology, right? There's a lot of optimization that says, let me preserve distances, let me preserve the statistics like covariances and stuff, but we don't have a good way of saying, let's preserve the topology. Like, what does that mean, right? Like, this means, for example, preserve cohomology. So that's why we used it. But I think the door is wide open for people to come up with methods that are specifically tailored at preserve topology. Yeah.
So this correspondence between vector bundles over a space and maps out of the space into the Grassmannian is really cool. I hadn't heard of that before today, and it seems like it plays a really essential role in this project. I was wondering, does that get used in other places in topology? Where else does this show up?
Yeah, so, you can replace, I think it's the role of the orthogonal group, ON, right? As the group of symmetries you're using to glue together local information. If you replace ON by another topological group, G, then there is an equivalent thing to the Grassmannian, and it's the classifying space of the group, which you've probably used in your constructions. And now maps from my space to the classifying space BG is the same thing as principal G bundles over B, right? So it has the same flavor. And the only reason why we went with vector bundles, i.e. the orthogonal group, is because of all the algorithms that work with matrices, right? The same is not true for like general Lie groups. So it's just a matter of sort of what algorithms are good for alignment. Yeah. Yeah.
Any other questions?
I mean, we can chat.
Yeah, let's thank Jose again.